So the last type of biasing circuit that I'm going to discuss is something called self-biasing. So basically the idea is that we don't have a separate circuit at the base side to do the biasing. Here I'm just basically branching out something from the collector, and I have an extra branch that goes to the base, and then I'm going to basically claim that this is going to give me good bias, or I can actually set the RB and RC in a way that it can actually properly bias my transistor. So the way that this works is that I can just write V collector, or Vy here, is equal to VCC minus RC IC. And then from there, I can say that basically, I can also say that Vy is equal to RBIB plus VBE. And instead of IB, I can write RB times IC divided by beta plus VBE. Therefore, I can combine these two, and I can write IC is equal to VCC minus VBE divided by RC plus RB over beta. Okay, and this is how I actually set the collector current using this self-biasing circuit. Basically, all I need to do is that I start with guessing. So guess VBE, same as before. And then based on this VBE, you go to this equation. It gives you an IC, and then use this IC, and then feed this IC to VBE equal to VT over VT ln of IC over IS. And then we're going to calculate the new VBE, and then we're going to reiterate until we get the accuracy that we want in our calculation. Okay, so there's nothing new in terms of like basically circuit analysis here. It's just another way to bias our circuit. You can look at this equation and you can appreciate that one interesting thing is that beta variations is not going to change IC by much. Imagine that RC and RB are the same order of magnitude. You can imagine that if beta is 100, then going from 100 to 150 is not going to change the value of RC by a lot. Okay, it's just going to change the denominator by a very small percentage. And then similarly, if you look at the textbook, I'm not going to discuss the self-biasing resistor because a lot of discussions are going to be very similar to what we have had up to now. So what I would do is that I suggest you guys to read examples 5, I think 12 and 13. Let me double check. No, 13 and 14. So 513 and 514 from the textbook. These are the example circuits for the self-biasing circuit, and you're going to basically learn how to analyze this. It's basically all these, it's all based on these equations that I wrote here, which are coming from basic KVL. Okay, one very important and very interesting feature of this circuit is that it is always, you can always guarantee that this circuit is in saturation. And the reason is that because the base current is always in this direction, and this means that I always have a current in this direction, meaning that here's positive, here's negative. Therefore, Vy, I can be sure that it's always greater than Vx, right? Simply because the current is in that direction. Therefore, there's a voltage drop on RB. And knowing that Vy is the collector voltage and Vx is my base voltage, I can be always sure that V collector is always greater than V base. Therefore, the base collector diode or PN junction is always reverse biased. Okay, so I'm not talking about deep saturation and checking that VCE is greater than 0.2 or not. This is basically talking about the soft saturation, and basically starting at the edge of saturation. You don't even get to the edge of saturation simply because your collector voltage is going to be always greater than the base voltage, so that PN junction between collector and base is always reverse bias, which is a great thing. So one interesting property of the circuit is that you don't really have to do any analysis on the fact that you don't have to really verify that your circuit is indeed in the forward active region. It's always, you can be always sure that you are in the forward active region, and basically this circuit is saturation proof. Just a quick summary of all the biasing circuits that we've seen. So we started with this simple biasing, and we saw that it's sensitive to beta variations. Then we moved on to this improved version, which was the resistor divider biasing, and we saw that it is it is beta independent, or like basically it's much less sensitive to beta variations, but then it is still it is sensitive to R1 and R2 variations, therefore like VBE variations and all that. And then from there, we actually had we introduced two different circuits. One that is basically based on the resistor divider with emitter degeneration, which is used a lot in practice, and it's very popular. And we learned a lot about designing this. And then we also learned about this self-biased circuit, or self-biasing circuit, that again is not sensitive to resistor variations or to beta variations, and it has this interesting feature of being always in the active mode. But it's not really it doesn't give us as many degrees of freedom in terms of designing R1 and R2. You don't have a lot of parameters or a lot of knobs to kind of adjust to get to the exact biasing condition that you want. It's a little bit more complicated to design, therefore that's why this one is actually more interesting to or more popular in terms of use. But then, well, the self-biasing is always interesting, and it's sometimes it's always good to know how to analyze it. So same as everything else, with PNP transistors, we're going to have very similar kind of discussions compared to NPN. So we pretty much have all those different circuits in PNP as well. So this is the simple biasing, this is the resistor divider, this is with the degeneration, and this is the self-biased kind of a circuit. So you can see that when you have, again, when we're talking about emitter degeneration, we put the resistor in the emitter, but this time the emitter is on the top because, well, emitter of a PNP is actually here, right? This is the circuit with resistive divider. Remember that this time, like for example, if VCC is 2.5 volts and you want a VEB of, let's say, 0.8 or 800 millivolts, then this has to be, the voltage at here should be 1.7 volts. So R1 and R2 should be set to get a 1.7 volts. This is why I was telling you that you cannot use a battery to actually do the biasing, simply because these values could be changing by a lot. You might actually have 0.7, 0.8 for NPN, and then 1.7, 1.8 for or 1.6 for PNP. And then if you have double transistors or multiple transistors, you might have many different kind of values here. That's why we need to actually do biasing, and we need to learn biasing circuits. As for the simple biasing, again, it's very similar to the idea that we had before. This time, emitter is connected to VCC, collector is connected to ground, and then basically you can imagine that Vout is actually always coming out of the collector side of the transistor. So similar to the NPN, Vout is always at the collector side, but well, not always, at least if you want to be similar to the NPN transistors, if the Vout was at the collector there, Vout is going to be at the collector here as well. Okay, but then for the simple biasing, as I was saying, the resistor is going to be at the base, similar to what we had at the end with the NPN. The difference is that the base resistor was connected to VCC back there, and it was actually, we wrote the KVL from VCC and then through the base resistor all the way to ground at the emitter. Here we are actually starting from VCC at the emitter here, and then we write the KVL again through the base emitter junction. So pretty much everything is the same, except that it's kind of like basically the transistor is kind of like flipped. So emitter is on the top, and collector is at the bottom. Emitter has a higher voltage than the base and collector, and basically whatever we have talked about the differences between PNP and NPN transistors apply. But other than that, the ideas for the biasings are exactly the same. If we want to see more circuits with PNP, examples 515 to 518 of the textbook are about these kind of circuits.